question paper.
Yes, sir.
Okay, so I'm going to discuss the solution with the solution of this particular question paper, with the examination of which was taken, uh, and the question was set on the topics of linear algebra and the Friedberg book, section 1.1 to section 2.1. All the questions were actually placed from there. Now, um, first of all, the participant who is present here, as I am showing him the question paper, and he requested me to know what were the correct answers. So I'm asking him to write in the chat box what option he opted for question number one. So write in the chat box what you opt for question number one. Yeah, okay. So B is the correct answer. It is all right, but I need to discuss a few things about this question. Why B is the correct answer? I asked you which of the following statements is incorrect. So it is statement two. I don't know what is your logic. Why did you tick on B? But since I'm discussing all the questions, so let me talk about why these statements 1, 3, and 4, these are correct statements. If we go by the section 1.2 of the Friedberg book, we have seen here that the n tuples, the set of all n tuples, which we denote by Fn, is a vector space over F. So where capital F is the field. Okay, so uh, that's why we already know that this, if Q represents the set of rational numbers, then it is easy to verify that capital Q is a field. And if F is vector space with respect to the coordinate wise addition and scalar multiplication, then in place of capital F, if you substitute capital Q, that is set of rational numbers, since capital Q is the field, and if you consider small n to be 1, then capital Q is a vector space over Q. Just like this becomes a special case of the statement that Fn is the vector space over F. So therefore, with this logic, capital Q is a vector space over Q. And with that same logic, statement 3 is also true, that R is a vector space over R because R is a field. But statement 4 is something different. It's because statement 4 actually doesn't come directly from that logic. Statement 4's proof is actually very difficult. Capital R is indeed a vector space over the set of rational numbers. But you see in capital R, one of the elements is root 2 like kind of things. They are irrational numbers. But what it is saying that we are going to take scalars from capital Q, and we can uh, satisfy all the properties of this particular set. Capital R will satisfy the properties of the vector spaces. The proof is very difficult, so I'm not going to discuss about the proof, but I can at least say that this particular statement, that capital R is a vector space over the set of rational number, this is a very important statement from the perspective that since it is true, therefore we can represent R, the numbers present in R, with respect by decimals. Decimal representation of real numbers is possible because this statement 4 is true. That is, R is a vector space over Q. So this particular result is very important, but it is not actually coming from the statement that Fn is a vector space over F, because in that case, F, in both the cases, in Fn and in F, both the cases, the F is same, but here this is not true. So it is actually, proof is actually very difficult. If you get hold of this proof sometime, later, then you can go through that. But I think that it will be much difficult for you to understand at this particular point because it requires lots of real analysis. So, but you have to remember this result and remember always in mind, keep always in mind that this particular, because of this particular statement, we can represent real numbers with respect to decimal, we can give decimal representation to the real numbers. So therefore, statement 1, statement 3, statement 4, all are correct statements. Only remaining statement 2 seems to be incorrect. But why it is incorrect? I shouldn't judge it in this manner that statement 1 and statement 3 and statement 4 are correct statements. So therefore, the remaining one must be incorrect. Maybe it may so happen that my question is wrong. So you have to judge it mathematically. Why capital Q is a vector space over R? Is not a vector space over R because we cannot generate a rational number by the elements of capital R, because capital R contains 2, say for example root 2. Okay, root 2 is an irrational number. Now, so for example, if I consider the scalar from, since I'm considering R to be a field over here, okay, so I'm choosing a scalar root 2 from this, and I'm choosing a rational number from the set of Q, which is a vector, say small r, and root 2 into small r. Any irrational number when multiplied by a rational gives you a rational number. So here, with respect to scalar multiplication, it is actually not satisfying the property of the fifth property of the vector space. It is not closed with respect to, not fifth property, it is not satisfying the closure property with respect to scalar multiplication. Any number chosen from the vector space, which when multiplied by the scalar quantity chosen from the field, their multiplication must be vector and it must belong to the same set. But here I'm choosing the scalar from the field R, which is root 2, and a vector m from the rational number, and I'm multiplying root 2 by m. So product of two, one irrational number and one rational number is irrational number, and therefore this irrational number, this vector, new vector root 2 m doesn't belong to Q because it is not rational, and therefore this is not closed with respect to scalar multiplication. Therefore statement 2 is incorrect statement. So that is the logic by which statement 2, option B, will be the right answer. Now I ask the candidate what he opted for question 2. Write your option that you opted for question 2. Okay. Okay, so this here, in this particular case, let V denote the set of ordered pairs of real numbers A1, A2, B1, B2 are elements of capital V and C belonging to R with these operations: A1, A2 plus B1, B2, and A1 plus B1, comma A2, B2, C A1, A2, C A1, comma A2. This is the operation. So I think I cannot, whatever your option is, first of all, let me tell you that your option is correct option. The option you opted for option D. It is correct option, and uh, because of both additive identity and additive inverse actually exist. Here, one particular student once pointed to me that two options look very similar. So for example, I wrote here in option A that additive identity exists, but additive inverse does not exist. And you look at option C, I just reversed it. Additive inverse does not exist, but additive identity does. Actually, option A and option C are actually same. Maybe I wrongly placed it, but that will not create any problem because these options are not correct options. So once you get your correct option, if it is not in conflict between small a and small c. So suppose small a is the correct option, then you may ask me this question that, sir, small a and small c looks very similar. They are actually very similar statement. So if one person ticks in c and one person ticks in a, both are going to get the same mark, that both of them are correct. But since I'm not worried about this particular printing mistake, because neither of these options a and c, although they are same, they are not correct options. Correct option is D. So here also I must tell the candidate that he is right. But are you sure? Are you sure about it, or you are just guessing that it has to be right? If you are not sure, then I'm going to do some board work for this. Do I have to? Shall I have to do some board work? Do you need some board work for this? Okay. So just a minute. Now the operation was a1 comma a2 plus b1 comma b2 is equal to a1 plus b1 comma a2 and b2, and the second operation is c of a1 comma a2, that would be ca1 comma a2. I'm talking about question number 2. I need to find, first of all, we need to find a number which will act as zero vector. So we need to find the zero vector. If zero vector exists, we'll say that additive identity exists. So since we are not, we do not know what is the zero vector, what is the form of the zero vector here, but we know that since capital V is the vector space of all ordered pairs, since it is the vector space of all ordered pairs, so its elements will be all pairs, ordered pairs. The vector space V contains elements of this form. Okay, I goes from 1 to 2. And since it is so, the zero vector, if I denote this by 0 bar, it is also of the form of ordered pair. But since we do not know it, let us put R1 and R2 in place of the zero vector. Let it be zero vector. So we have to find what is the form of R1 and R2. The characteristic of zero vector is such that when we add a zero vector to the non-zero vector, the result must be the non-zero vector. That means the non-zero vector doesn't change. So this implies, now I have to use this operation as it is given. So you see the first element of this sum is a1 plus b1. I am adding the first element of these two pairs. So here that will be a1 plus r1. And the second elements are getting multiplied. So I must write a2 r2. So this becomes an ordered pair, and that is equal to a1 and a2. And if I equate this to, if these two pairs are same, so the first element of the pair is similar to the first element of the right hand side, and the second element of the pair is similar to the second element of the right hand side. So now all these things are real numbers, and since they are real numbers, we can cancel it from both the sides. So this implies that your r1 is equal to 0, and this implies we can divide both the sides by a2, because here a2 is not 0, it's a non-zero element. Here a2 is a non-zero element. A2 is non-zero and a1 is non-zero, and therefore we can divide both the sides by a2, and so r2 becomes 1, and therefore the zero vector r1 r2 has actually the form 0 1. So here 0 1 is actually the zero vector of this. So we see that zero vector exists, and it's of the form 0 comma 1. You can take any element from this vector space and you can add this to the element. You will find this element is not changing, so it is the zero vector. So additive identity exists. So additive identity is present. Once you get the additive identity, then you need to find what is additive inverse. So in that case, since I do not know the form of the additive inverse, let us now uh, assume that for the element a1, a2, the additive inverse is a1 prime, a2 prime. And additive inverse are in such a number which when added to the original one gives you the zero vector. So this element must be 0, 0, 1, because 0, 1 is my zero vector here. So this implies if I again apply this rule, so I get a1 plus a1 prime is equal to 0, and a2, a2 prime, that is equal to 1. Okay, and now you see, since all these ai's and ai primes are real numbers, so this gives you a1 prime is equal to minus a1, and a2 prime is equal to 1 by a2, and a2 is not equal to 0. Therefore the zero vector of an arbitrary element a1, a2 is actually minus a1, 1 by a2. So this is the zero vector. So sorry, not zero vector, additive inverse. This is the additive inverse for the non-zero vector a1 prime, a2 prime. So here we see, from this calculation we see that additive inverse also exists. Additive inverse also exists. So therefore we have the option is I'm going back to the PDF file. I'm stopping the share. I have saved this board work. If you need it, and I can send it later on. So because of this, I must say that your option, your reply is correct, that both question number 2 has both additive identity and additive inverse. Now let me ask the candidate, what is your answer to the question 3? What did you opt? A. Why it is A? Because if you see the Friedberg, you will find that what is the question? Let us consider a square matrix of order 2, 3, and the matrix elements are chosen from a finite field with a characteristic 2. Then the total number of matrices in the specified vector space would be what? Now this is a result. Actually, I am referring to all the candidates to exercise of section 1.2, the last problem, maybe the problem number, probably the problem number 24. And I did this problem in the class where I actually explained that I explained that if you consider a finite field Z2, if we consider a finite field Z2, which contains the two elements 0 and 1, how many elements are there will be in the matrix, in the vector space of matrices of order m by n, and you know the formula is 2 to the power mn, 2 to the power mn. Now here I have chosen a square matrix where small m and small n are same, and therefore that is according to the question it is 3. So according to the formula, the total number of matrices present in this case will be 2 to the power 3 into 3, that is 2 to the power 9, and 2 to the power 9 is 512, and so this option is also correct. Now actually a result has been used in question number 3, and that is the result. This proof is as a result it is present in exercise of section 1.2. Now I'm asking the candidate which option he opted for question number 4. D. Okay. Why D? Why it is D? It is because its explanation is very simple. This idea has been chosen from section 1.1. I am trying to explain this without any board work. You will understand. O is the origin. Capital A is some point where it has coordinate x1 comma x2, and B is the some point on which has some coordinate. Okay, some coordinate. Now you see, I am actually interested in the diagonal OC. Now it is a known fact that if I consider this OA to be the vector x and this OB to be the vector y, then this diagonal is actually represented by x plus y. Okay. Now to get a diagonal of the parallelogram, we need two vectors, x and y. Without x and y, you cannot represent the diagonal, which is x plus y. So you can say that if I choose this set x comma y, okay, so its linear combination 1 into x plus 1 into y, that is x plus y, is the diagonal. So definitely xy is the spanning set of the diagonal OC. X by 2 and y by 2 is also a spanning set of the diagonal OC. Why? Because you see, if we choose this element x by 2 and y by 2, and if I multiply, if I take the linear combination of these two as we choose the scalar 2 and we write it as 2 into x by 2 plus 2 into y by 2, then that also becomes x plus y. So that this set is also a spanning set of the diagonal OC. If I choose this set twice x and twice y, and if I choose the scalar half, then the linear combination half into twice x plus half into twice y gives you x plus y. So that also becomes a spanning set of for the diagonal OC. And therefore these three sets A, B, C are the spanning sets of diagonal OC, but 0y is something different. Here, since the first element is 0, no linear combination of it will represent the diagonal OC, and therefore 0y is the incorrect option. So you have opted for D, that is true. Also, you can use one of the results of the book, which states that if a set UV is the vector space, I mean, sorry, I did this particular problem in one of my classes, that it is there in the chapter of linear combination, that if a set containing two elements u comma v is a spanning set, then au comma bv is also a spanning set. Probably you can remember, if ub is the spanning set, au comma bv is also a spanning set. Any scalar multiple of these two will be a spanning set. So with that reply, with that result also, you can say that your option D is the right option. So here also you are correct. Now what about question number 5? Yeah, that is one option. That is one option which you did wrong, and I think that this part for question number 5, you opted for small a, but it is wrong. It is not a. It is actually b. So I think that I have to do some board work for this particular problem. So let me quickly do this board work. Okay, so where is the question? Because I need to probably, yeah, okay, fine. So let us do it. This is a, you can note that this is the one wrong option, wrong entry by you. Okay, so why it is option 2. So the question is, question was v is equal to Rn, and you know Rn is the set of all ordered n tuples, and the set S contains these elements e1, e2, dot 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 ek, where k is lying between 1 and n. Okay, and ej, the vector, the element ej is actually of the form 0 0 0 0 1 0 dot 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 0, and j lies between 1 and k. Okay, and it is written in the question that 1 at the jth place, 1 at the jth place, it is written 1 at the jth place. Achha. Now if to make you understand this particular option, to make you understand this particular problem, I need to reduce it into a two-dimensional case, let us consider V equal to R2. Now, if I select S, S contains the standard ordered basis which is represented by E1, E2. I am considering the special case of this particular problem to understand it. Now, what will be E1? According to this, carefully observe that EJ is of this particular form, and here 1 is at the jth place. And you see here K, if you consider K, the suffix K is lying between 1 and 2. K is lying actually between 1 and 2. K chooses value from 1 to 2. Now, E1, E1 means the first element will be 1 and the other element will be 0. E2 means the second element will be 0 and the second element will be 1 and the first element is 0. It comes directly from this definition. And therefore, S is actually 1, 0 and 0, 1. Okay. Now, since we already know that it is a basis, we have already proved it. It is a linearly independent set and it is a basis. So if you choose any vector x from R2, x is of the form x1 comma x2, and you see that this can be easily represented as a linear combination of these two linearly independent vectors. And therefore, any since small x is arbitrary, any vector of R2 is expressed as linear combination of these two. Therefore, this implies x belongs to LS, and we already know that a spanning set is always a subset of R2. From here, we find that R2 is a subset of the spanning set, and together they imply that LS is actually R2. LS is actually R2, and therefore R2 is getting spanned by the set capital S. Now you generate your this particular concept to R3, to R4, to R5, and therefore it is also true for Rn. And so LS equal to Rn is the right answer. I hope you have understood why it is true. I will also send you the board work for your better understanding. Okay. So I'm stopping this share. Now, you opted for question number 6. Question number 6, you opted D for question number 6. Okay, what is the question number 6? Question number 6 was the set of all polynomials with coefficients from the set of real numbers is denoted by PR. We consider the set W equals to fx belonging to PR and fx equal to 0 or fx has degree n. Which of the following is incorrect? Now, the options given are W is not a subspace of PR, W is not closed under scalar multiplication, and 0 polynomial is a member of W. Now, this particular problem is actually a problem taken from the exercise of section 1.3, that is the exercise of subspace. And in the very beginning, this problem is there. Probably you have seen this particular problem. Here, if you have done this problem, I once discussed this problem in the class, that W is actually not a subspace, is not a subspace of the vector space PR. PR is the set of all polynomials whose coefficients have been chosen from the field of reals. Okay, that is PR. So W is not actually subset of PR, and since I want an incorrect option, so W is not a subspace of PR is the correct option. So therefore, this answer option will not be. This is not an incorrect option. So option A is not right. In the sense that I wanted to find incorrect option, not the correct option. Okay. W is not closed under scalar multiplication. That is also true, and that is why W is not a subspace of PR. So it is also true. W is not actually closed under scalar multiplication, and therefore this option is not the incorrect option. Zero polynomial is present in zero polynomial is definitely a member of W, and therefore here it is written that zero polynomial is not a member, is a member of W. It's an incorrect. I'm writing here zero polynomial is a member of W, and it is true. It is a member of W, and therefore it cannot be incorrect option. So all the options given over here in A, B, C, they are not incorrect options. Actually, they are correct options, and therefore the incorrect option is none of the above. So you opted for D, and that is it is true. What you opted for question number 7? You opted for B. Now I must say that this is one of the another mistake which we have done. This correct option here in question number 7 is not B, it is actually D. Why? Let me talk about it. So you can mark it. You have opted for B, but B is not the right answer. Let us consider the vector space R2R. Why R2R is a vector space? Because FNF is vector space. Let us consider the two subspaces of R2R. This subspace you have already dealt with. This is the x-axis and this is the y-axis. Then which of the following is a correct statement? Now what is written? Two-dimensional space is a linear sum of W1 and W2. Means any two-dimensional point can be expressed as a sum of these two sets. It is true. This part is true, but cannot be expressed as the direct sum of these two subspaces. This is not true, because why it is written that it cannot be expressed as a direct sum of these two. When we say that a particular vector space is a direct sum of two subspaces, if the element of the vector space can be expressed as the sum of the elements chosen from individually from the two subspaces, and the intersection of the two subspace contains the zero vector. But you see here, if I take the intersection of this W1, this x-axis and y-axis, the intersection is the origin. But origin is present in W1 and W2, both in W1 and as well as in W2. Because if you choose, since small a is any real number, so 0 is also a real number. So 0 is a member of W1. Small b is any real number, so small b could be 0 also. So 0 is a member of W2, and therefore 0 is present in W1 and 0 also present in W2. So W1 intersection W2 is the zero vector, and therefore W1 and this 0 is actually present in W1 and W2 intersection. So actually, this two-dimensional space is linear sum of W1 and W2, and W1 intersection W2 is not phi, and therefore actually two-dimensional space is the direct sum of W1 and W2 by definition. So therefore option A is incorrect. 2D is direct sum of W1 and W2, but cannot be expressed as the linear sum of these two subspaces. It cannot be true, because to be a direct sum of two subspaces, it has to be linear sum first, and therefore this option is if you are saying that a particular vector space is not linear sum of W1 and W2, but it is direct sum. That is not true. Just go through the definition of direct sum from section 1.3. Okay, in the exercise it is given. So this option is not true. Two-dimensional space is a linear sum of W1 and W2, but origin is not contained in the intersection. Actually, small a and small c, these two options are similar. Here I am saying indirectly that cannot be expressed as a direct sum, means I am saying that W1 intersection W2 contains no element, but here origin is actually contained in it. I've already explained, and therefore option C is incorrect. So only I can say that this option is correct option. There's two-dimensional space is the linear sum of W1 and W2. That's it. So option number D is the right option. Have you understood? I'm asking the participant, have you understood? Yes, okay. Now what you opted for question number 8? What was your question in question number 8? C. Phi is a basis of 0 bar. Okay. Now, yeah, obviously it is true, because 0 bar is your option is correct. This here in this question number 8, the correct option is C. It is because 0 bar is the vector space, and span phi is equal to 0 bar. Okay, and this result is a well-known result. Okay, and phi being the empty set is linearly independent. I proved it in the class that phi cannot be empty set, cannot be linearly dependent set. uh, because if I consider phi the empty set to be linearly dependent set, then it must contain an element, so that any scalar chosen from the field multiplied by the element of phi gives you 0, where the scalar is actually non-zero, which comes from the definition of linear dependentness, but phi contains no element at all. So from this contrapositive argument, our assumption that phi is linearly dependent, it is wrong, and therefore phi is linearly independent. So empty set is linearly independent, and its span of phi is 0 bar. Therefore, together this actually gives you that phi is a basis. So if you have, while opting for this option, if you have understood correctly, and you have thought of all possible parts of the definition, then you are right. Okay, option C is the right option. Question number 9, what you opted? C. C is the right option, because I'm not going to explain this thing here, because this particular this particular question has been chosen. I have made this question keeping in mind a result. I do not have, I cannot recall right now. Um, Probably in the exercise of linear independence of Friedberg, section 1.5, I think, this particular result is present. That columns of this, if I consider this upper triangular matrix, square upper triangular matrix, all its columns are actually linearly independent. This proof, you have been asked to prove that this result in the exercise. Yeah, it is there in section 1.5, last but one, I think. What is the question number? Can you send me the question number so that I can say it in the video, so that the people who will be seeing the video later, they can go there and check it. In section 1.5 exercise, this result is there. I want you to tell me the question number so that I can say the question number in the classroom, because I do not have the book with me. That result has been given as a question in question number 9, and you opted for C. So this is the right option actually. Now, what you opted for question number 10? D. Question number 10 is D. Have you got the question of exercise section 1.5? The question where this question number 9's result is there? If not, then okay, forget. People can find it. We have mentioned the option section 1.5 correctly, then people can find it by themselves. So question number okay. No need to worry. Question number 10, you opted for 2-1. 2-1 is not linearly. No, actually, this is also a kind of question which is tricky, and therefore this option, question number 10, this there you did another mistake. This is not a right option. You opted for question number D. Question number D is not actually right. It is not right. Question number D, it is written 2-1 is not linearly dependent. Now, why it is not right? Let me say, because the problem here, it is given that R2R is the vector space and this is the basis. Then which of the following is not true? Which of the following is not true? Now you see that any vector, any set, how do I, here I can say that you can apply some kind of IQ over here to opt for the correct option, but you are going to opt for the correct option by negation. I mean, I'm going to eliminate the options which are not actually correct. Okay, although I do not like it, but I'm going to do it over here. And if you want to go in a usual process, then you have to consider this particular set, and you have to, and that you must do, that you have to consider this to this is this set, and you can choose scalars from the set of reals, and you can two scalars a and b, and you can multiply the first scalar by this element and the second scalar by this element and equate it to 0 0. You'll find that both the scalars are 0. So this set will actually be linearly independent. Yeah, the question number 9 in chapter 1, section 1.5, I'm asking all of the students to check question number 17. In question number 17, this result stated in question 9 of our question paper is given. So question number 17, that result is also very important, and you need to, I ask all of you to prove this result. And it is also important, the result question number 17 is also important from operator theory's point of view. Now you can easily check that this particular set is a linearly independent set. Okay, actually this set is linearly independent set. Okay, and any singleton set, any set containing singletons, single vector. This result is also there in this particular chapter. Any singleton set is always linearly independent. Any singleton set is always linearly independent. Oh, why? Because if you consider a set which contains a non-zero vector, only one non-zero vector, and you choose a scalar quantity and you multiply the scalar by the non-zero vector, okay, and you equate it to 0, then obviously the scalar must be 0. And that gives you that the vector is actually not linearly dependent, it is linearly independent. But what have I mentioned over here? That this is not linearly dependent. If a set is not linearly dependent, that means it is linearly independent. So I am actually stating the right option here. It is definitely not linearly dependent. And question number D, by the same logic, question number D, since it contains, no, option number D, which since it contains single vector, it is also not linearly dependent. So this option is also true. And R2R is the vector space over a field whose characteristic is infinity. This question mark is a printing mistake. I beg pardon for this. R2R is definitely a vector space, and characteristic of R2R is actually infinity. Okay, the characteristic of the field. What is the field over here? The field is car, and characteristic of R is actually infinity. So this option B is also true. And I explained in my one of my classes why R, the field of real numbers, is in characteristic of field of real numbers is infinite. If the characteristic of field is not 2, if you try to recall the definition of characteristic of field, finite field, then you will understand. And it is also given, this particular question, this thing is also given in appendix, where field has been, a few lines of about field has been written. So definitely R is a field which with characteristic infinity. So this is also correct option. But here 2 1 and 0 minus 1 is actually Li set, but here I have written that it is not Li, and therefore you can check it by yourself. I'm not going to do any board work for this, and therefore this option is the incorrect option. So correct option will be small a. That is question number 10, correct option is small a. And what you opted for question number 11? In question number 11, you opted for A. Yeah, it is true. I'm not going to explain this because this result, although written in a very clumsy way, actually it is the statement of the replacement theorem. Okay, I have actually, if you use the replacement theorem, you will get to see that if L contains 1, 2 is any linearly independent set, RT will contain a number with only one vector in it. So actually the replacement theorem is the application of replacement theorem has been asked over here, and therefore the number of vectors will be one, actually one vector. Try to get to see the replacement theorem from the chapter of basis, and you'll get to know why it is the answer is one vector. And your option, you also opted for A, that means you know it the result, so it is a true, a correct answer. What you opted for question number 12? Exactly, exactly. None of these is the correct answer. Question number D is correct. None of these. Actually, the as you are writing, correct answer to this question will be 5 minus 3 and 16. 5 minus 3 and 16 will be the correct answer. So how do we actually, okay, do I have to show board work for this particular problem, or people can understand? What is the general I mean view of your class with respect to this question? I did one problem of similar type in one of my class, where you have to do what you have to do, that you have to select the basis of R2, and R2's basis is what, uh, 1 0 and 0 1, and you have to find the transformation. You have to find the transformation. Actually, you need to find the transformation over here. You need to find the transformation, and because actually, okay, okay, so then you are saying that it can be done by using thinking. No, I'm actually saying that it kind of process is very not okay. uh, by thinking you can do it. You can do one thing. The easiest option will be, you can express you can express 1 1 in terms of the basis element of R2. So I can write, in place of 1 1, I can write 1 into 1 0 plus 1 into 0 1. So t of 1 1 is actually becoming t of 1 0 plus t of 0 1, because t is linear. So you have got your equation, you have splitted your equation left hand side in this manner: t of 1 0 plus t of 0 1 equal to 1 0 2. And t of 2 3 can also be expressed as linear combination of 1 0 and 0 1. Okay, and therefore we can write it as t of 2 into 1 0 plus 3 into 0 1. So I am getting two equations in terms of 1 0 and 0 1. And by solving them, we can easily find, by solving these linear equations, we can easily find what is t10 and what is t01. Once you get what is t10 and what is t01, you see that 811 can also be expressed as linear combination of 10 and 01. So I can write it as, I can write 811 as 8 into 10 plus 8 into 11 into 01. So t of 811 will be t of 8 into 10 plus 11 into 01. And by linear transformation property, we can write it as 8 into t of 10 plus 11 into t of 01. We can substitute the value of t10 and t01 over here. And the answer of to this question is actually 5 minus 316. None of this option is not present in this any of these four options, and therefore none of this is the right answer. Yeah, okay. You are saying that since people will not be able to see the chat box, so I'm reading it, that what you have written in the chat box. So you have written that candidate present, participant present over here has written that we need to solve, to do it. I mean, if one solves questions from linear transformation, he can easily solve this, sir. Then has put a smiley, and it's like applying backtracking algorithm. We can do direct as well instead of 1 0 and 0 1. In many ways, the problem can be done. So this is the opinion of the student, and so I'm happy to hear his opinion. That he is actually very confident about this, and therefore, yeah, whatever you like. And what you opted for question number 13? No. Question number 13 is option is B. That is another option which you did incorrectly. So I need to do a board work for this. Okay. Now you have opted for B, that is 100, and it is not true. So let us, I think that we need to do kind of board work over here. So in this question, it is given that we consider a 10 by 10 symmetric matrix. That means this particular problem has been chosen from the example of the chapter of basis. If you consider an n by n symmetric matrix, okay, what will be the dimension of that? And if that W contains, the n by n contains the set of n by n symmetric matrix, set of n by n symmetric matrix, what will be the dimension? What will be the dimension of W? This result is there in example. One of the students, just before the exam day, he called me to discuss this particular problem. So dimension of W, it is given in the book, it is given half into n plus 1. So this is the result. So if I choose n equal to 10, so for 10 cross 10, it will be half into 10 into 10 plus 1. And therefore that would be, which is 55. So this 55 is given in option A. So option A is the right option. Now, if you ask me, sir, why this answer is n into n plus 1, now you see that when we make a symmetric matrix, we first choose the diagonal element AB, and a number is chosen over here C, which is similar to the number chosen over here. So actually, uh, the element A12 is similar to element A21. So to make symmetric matrices of any size, we have to first consider diagonal element. We have to consider diagonal elements, and then we consider this part and that part and that part and that part. These parts are not required because this part will be similar to that. Okay, so if I can, you see that these diagonal elements can be filled up. This diagonal elements, this diagonal line can be filled up in two ways. There are two ways by which the diagonal element line can be filled up. And just above it, for 2 by 2 case, there is only one option. So for 2 by 2 case, it is what? 3. Now, for 3 by 3 case, let us see, you have three options for these diagonals, 1 2 3. Then you need to fill up the upper portions where you have two options, and then you need to fill up the next upper, that is 3. So here in for 3 by 3 case, first option is 3, plus second option is 3 minus 1, and the third option is 3 minus 2. And therefore the total number of option is here is which is 6. Now in this manner, if I consider the n by n matrix, so for diagonal we have n choices, for diagonal we have n choices, then upper portion can be filled up in n minus 1 ways. Next upper can be filled up in n minus 2 ways, and ultimately you can go up to 3 plus 2 plus 1. And you know the sum of this is half into n plus 1 from AP series, and therefore this is the right option. So this application has been asked in the examination. Probably you have understood. I have saved the board work. Later I can send it to you. And let us stop the share and let us go back to the question. Okay. Question number 14. What was your right option? No. No. Question number 15, for question number 14, that is another wrong, another mistake which you have done. Here the incorrect option is all the options A, B, C, E are correct options. Only incorrect option is option number D. In Euclidean 3 space, the subspace of dimension 1 is line. Now, a few days ago, I had a chat with a student of CSE section A, and he told me that he isn't familiar with the Euclidean space, but he has never heard of this word Euclid. Heard of the name of Euclid actually. But see, the Euclid is a geometer whose geometry you have done in school. All postulates about straight lines, triangles, theorems about squares, rectangles, everything which has been done by Euclid. And in coordinate geometry, you do this thing. It's kind of generalization. You do uh, the Euclidean geometry actually in coordinate geometry class. So actually you are familiar with Euclid. Euclidean three space is simply means Euclidean three space simply means three-dimensional space. Euclidean two space simply means two-dimensional space. Euclidean n space simply means n-dimensional space. Now, this option, this answer, question number 14, is I'm not going to explain this because I ask you to find the paragraph from the book where it is written, and all the lines written in question number A, question number B, question number C, and E. All these lines you are going to get from the Friedberg book. Probably in the chapter of basis. Probably in the chapter of basis. It should not be in the linear transformation. Probably in the basis. Yeah, since it is talking about dimensions, so at the end of the chapter, somewhere in the paragraph of the Friedberg book, this explanation is given to you. Only one line is missing from here there. Only one line that you will not be able to find is question option number D, and that is the incorrect option. So I ask all of you to read it from that paragraph. So that is one wrong option which you have made. Euclidean three space I have already explained. It is Euclid is a geometer who gave one of the great books by Euclid is Elements. One of the great books by Euclid is Elements, and I'm going to show you. It is a live class, so I'm going to show you something. Just wait. This is the book I'm actually uh, saying this Elements by Euclids. Okay, so it is a great book. Everything in this particular book that is there is actually we have learned in school geometry. So we did coordinate geometry in Euclidean space. You have done all this distance formula, etc., etc. Everything is because of Euclid. So Euclid is actually very known personality, just like Einstein in physics. Both the names start with E. Okay, it's a coincidence. So therefore, you have to be familiar. If you do not know this man, then you get to know you. I ask all of you to read Wikipedia and read Euclid and buy this book. I am actually marketing this book. Okay, you all have to read this book, Euclid's Elements. So therefore, but the question has not been asked from Euclid's Elements. The question has been asked from Friedberg, the chapter of dimension. Okay, we all do Euclidean geometry. Child, when learns geometry, does Euclidean geometry. After that comes Riemannian geometry, which is harder. But if you do not understand Euclidean geometry, you will not understand Riemannian geometry. Okay. Question number 15. What is your option? I'm going to say whether your option is correct or wrong only because this question has been done in the class. Similar type of problem has been done in the class. The correct option is, let me see. Yes, yes. The correct option is B. Here I ask all of you to calculate this. I'm not going to explain this thing because similar question has been selected from the chapter exercise of dimension, basis and dimension, and I did similar problem in the classroom. So I'm not going to explain that. Now the candidate who is present over here, he is saying that for question number 14. Oh, so the candidate is actually helping all of you. Since I do not have the book in front of me, he's saying that I must say that for question number 14, that means that Euclidean three space part, the Euclidean three space part, he is referring all of you to go to section 1.6 and example 20, not exercise, example 20. Below that, a paragraph is written on question number 14. So if you read that paragraph, then you will get to see why D is the right option and why this statement written in D is incorrect. So candidate is present right in by clicking this option 2 for question number 15. So it is okay. What you opted for question number 16? Obviously, because this is a result. This result I have chosen from the exercise of linear transformation. The trace of A, if I consider this matrix a matrix containing all such elements, all such square matrices whose trace has been considered, you can find this. I again ask the candidate to give me the question number, which is whose reference I must take for in accordance with question number 16, because if you have done this particular problem, you will see that for n by n matrices uh, with a trace, the answer is the nullity of T will be n square minus 1. This is a formula, that is n square minus 1. And in if n equals to 3, so by putting n equal to 3 in the formula n square minus 1, you will get 3 square is 9 minus 1, that is 8. So answer is B, and the candidate also opted for B. So in that respect, in this respect he is correct. No, he opted for A. Now A is not right answer. B is the right answer. N square by 2 is not the right answer. N square minus 1 is the right answer. Okay, so therefore this would be 3 square minus 1, that is 9 minus 1, that is 8. You can find this particular problem. This is an example which I have made out of this problem. The problem is there in section 2.1 exercise, linear transformation, Friedberg. It will be helpful if you find the question number also, so that I can declare it in this video. And meanwhile, you can tell me what is the right option for question number 17. No. Have you understood this? I have done Friedberg section 2.1, the reflection operation, reflection about x-axis and reflection about y-axis. So you opted for B. this is not correct, because let me show you this. If you can recall the reflection operation, so reflection operation is given in the following. This is the definition of reflection operation. uh, this is reflection about x-axis, reflection about x-axis. And if you can recall, the diagram was like this: a1, a2, and here also at a similar distance, a1 minus a2. Okay, and if I write reflection about y-axis, so that will be minus a1 comma a2. Now this is reflection about y-axis. Now you see, in both these cases you can easily show that this origin is actually present. Okay, so nt and nu, they both contain they both contain 0 0. They both contain 0 0, and therefore nt and nu, they are actually same. And if you carefully observe, you will find that if you choose any vector from this two-dimensional plane, any vector from this two-dimensional plane can be expressed as linear combination of, linear combination of this RT. RT, what is the definition? All such elements such that X belongs to V. That is the definition of RT. So if you carefully observe, geometrically try to think that actually RT will span the entire R2, RU will also span the entire R2. So here is actually RT and RU, they are same. So for reflection about y-axis, reflection, if I talk about reflection about y-axis, so you are actually getting all these sides. All these sides you are getting geometrically. And if I talk about reflection about x-axis, so you are getting all these sides. So in both the cases, you are getting your two-dimensional coordinate plane. And therefore here, the correct option is RT. Correct option is RT equals to RU. Okay. So that option also you incorrectly opted, and therefore uh, I have, by discussing with you, I have seen that out of this, all the questions you have attempted 7 questions wrongly, and therefore you have got your marks actually deteriorated. So I am pausing the video and I'm going to end my today's discussion over here. Okay, I hope all of you have understood.